Okay, guys, AP students, welcome to little mini unit we're going to do over organic molecules. The reason we're doing it now, we're not really going to have as much time, or I anticipate we'll be lacking a little bit of time towards the end of the year when we're going to do our review right before the AP test. So we're going to go ahead and do a small introduction to naming organic compounds, recognizing the polarity of organic compounds, kind of how they'll mix with water and stuff like that. And it goes well with the unit that we're in right now in bonding and intermolecular forces. So let's get started. So let me share my screen as usual. Get into the Zoom here. Okay. So we're going to go through and we're going to name some compounds, and we're going to look at some compounds, draw some compounds from name, and kind of see if we can figure out how to do these things. And then tomorrow we'll talk about functional groups and the polarity of molecules and their behavior, and which kind of goes along more with this unit. A lot of the stuff that we're going to talk about here, you will see on your AP exam, but you won't see formal questions. Organic chem is not really in the AP curriculum, although I love to teach it. It's a good introduction for freshman level chemistry and the college level. But you're not going to see questions about, not as detailed as what we're going to go through here, but you will see organic molecules and have to tell whether or not they're polar, whether or not they would mix with water, why one would have a larger boiling point than others, and that kind of a thing. But you won't be asked to name them. Nevertheless, so let's move on. So this is day one. We're going to talk about these, but what is organic chemistry? Organic chemistry is the chemistry of carbon. And so especially carbon, things that form four bonds, silicon, these form most natural substances. Silicon forms long chains and ring structures with oxygen generally. Can do it with just silicon, but usually with oxygen, and we'll talk more about that later. Carbon, on the other hand, forms chains and rings, generally with itself. It can do it with other nonmetals, and carbon is the basic structural unit for biomolecules that we have on Earth. And so what we're going to really focus on are not necessarily the chemicals of biology, but the organic compounds associated with carbon. So most of them just contain carbon and hydrogen, and we call those hydrocarbons. Organic chemistry is the study specifically of carbon-containing compounds. Yes, the chemistry of life molecules, but there are millions of carbon compounds. They can form single, double, and triple bonds, as you are aware, and that'll limit the number of bonds they have with other elements or other atoms if they are bonded to other carbons with more than a single bond. The first one that we're going to talk about, of the first set, are called alkanes. Those are also referred to as saturated hydrocarbons. The reason we say saturated is that they're covered in hydrogens. They're usually saturated with hydrogen, meaning there are no double bonds. So alkanes are going to be carbon-containing compounds that have only single bonds between the carbons. The ending here is what's important, and the ending is A and E. Ooh, that's not going to show up on there, is it? Let's do white. A and E's. And so these are going to end, the names of them, in A and E, like they're alkanes. So it would be like methane or propane or butane. Unsaturated hydrocarbons, which we'll talk about in a little bit, those will be called alkenes. But unsaturated hydrocarbons will have at least one double and or triple bond. So they won't contain all single bonds between the carbons. They'll have at a minimum one double bond or one triple bond. So if you look over here for these unsaturated hydrocarbons here, this one contains a double bond, so it's unsaturated. If you look at the one above it, which is all saturated, there are no double bonds between the carbon atoms. And so this will be reflected in how we name them in a few minutes. Okay, so yeah, the unsaturated ones are not saturated with hydrogen. They're actually going to have a double bond, which limits the amount of hydrogen present. So the simplest hydrocarbons are going to be alkanes, A-N-E. They're going to end their names in A-N-E. The general formula for them is CnH2n plus 2. So you'll have twice the number of hydrogens plus 2 for the number of carbons. Alkane melting and boiling points increase with the number of carbons. And this is true of all hydrocarbons, but as you get more a longer chain of hydrocarbons or a longer chain of carbons in the hydrocarbon, it's going to increase its boiling point. There will be more forces, more intermolecular forces between the molecules. They will actually be polarized electrons. So you increase the polarizability as you increase the number of electrons in the compound, the number of elements in the compound or atoms. So their polarizability will increase. And so their boiling points will increase as they go up. As they get smaller, they're more likely to be gases. And as they are larger, they're more likely to be liquids and solids at room temperature, that is. So alkanes, why would the melting and boiling point increase as the number of carbons increase? The answer is polarizability. So as you increase and have a larger molecule that contains more carbon atoms, it's going to have more electrons present and a greater polarizability that will be more polarizable if it is a larger molecule. So isomers of alkanes, you can have isomers of alkenes as well, but isomers are things that have the same chemical formula, but they have a different structure. So alkanes with 4 or more carbons can form this term isomers, or molecules that have the same atoms, but they're bonded in different ways. And so straight chained hydrocarbons can form long strings of chains, or they can have little groups off the sides. And I'll kill groups, but I'll show you what those are. A great example is hexane. Hexane is C6H14. And so here are a bunch of different chains of hexane. What I want to do is I want to draw some structural isomers of hexane for you. And I think you've got some space in your notes. But C6H14, if I were to just draw it with 6 carbons with the appropriate numbers of hydrogens around it, I would draw it like this. Now, there's a couple of different ways to draw these. You can have what are called structural formulas, which is what I'm drawing. And then you can have condensed structural formulas, which I'll show you in a second. So structural formulas show every single atom and the bonds to each of those atoms in the molecule. So this would be hexane. And it's got 6 carbons in a straight chain with hydrogens all the way around it. And that would total 14 hydrogens, CnH2n plus 2. So that would be one isomer of hexane. That would just be hexane. We would name this hexane. We'll get to the naming in a little bit. But there are other ways to draw this that still have the same formula of C6H14. So what I want you to draw is all the different ways that you can do it. I'll go through and do this. If you want to hit pause and try it yourself, go ahead. If you just want to watch me do it, I suppose that's okay for this one too. I'm going to draw it without the hydrogens so that you'll know that the hydrogens are what's at the end of each bond. But if I drew, say, 5 of them in a row, I could put a carbon on one of them. And then if I put hydrogens all the way around that, of course, carbon forming 4 bonds, you know, with hydrogens all the way around, it would look something like this. And in your mind, you can put those hydrogens around there. I'm not going to do it here. There is another place that we could have put that carbon. We could have put the carbon on the 3rd carbon there, right? So I could have drawn it with a carbon, a carbon, a carbon, 5 carbons in a row, and instead put that carbon on the 3rd carbon instead of the 2nd. This would be a different chain. So that would be the 3rd isomer of hexane, or 2 isomers of the original one for sure. But 3 different ways that you could write hexane with the same C6H14. If I moved it one more over, so let me just show you. If I took this off and I put it instead over here, would that be a different molecule than the one that's above it? So this one right here is a molecule, right? And the one down here, would those be different molecules? The answer is no, they wouldn't. They're just flipped. So remember, this is a 3-dimensional molecule. So I have a carbon on the 2nd carbon from the left. If I have a carbon on the 2nd carbon from the right, it's the same structure if I flip them around. So this is not correct. So that would not be, that would not actually be an isomer. So one there and one in the middle would be fine. So now my straight chain of 5 is over with. And in fact, what if I did this? What if I took this one off here and I put it on the 1st carbon? That's not any different than the first one I drew. The first one I drew just has a straight chain of 6. This is also a straight chain of 6. Remember, it's a 3-dimensional molecule. These are spinning on an axis. It would not likely look any different. It's just drawn differently because we're drawing them in 2D. So, oh, I drew that in the wrong place. Look at me. So it'd actually be on the 2nd carbon. Another way to draw this would be to draw 4 of them and have a carbon here and a carbon here. And I can put all the bonds around there. Another way to draw it would be 4 with a carbon on top and a carbon on bottom. And I think that's it. Is that, excuse me, I think that's all. If I did 3, I would end up, let's do 3. So if I ended up doing 3 carbons in a row, and let's say I put 2 on one side and 1 on the other to give me the total number of 6, this one and this one are the same. So there are only 5 isomers here, 5 different ways that you can draw it. Now, if I scroll back up and look, these are the ones that are drawn. Here are the 4 isomers of the original hexane. So there are 5 different ways you could draw it. One is the straight chain, and then these are all the branched ones. So we've got let me use a highlighter. We've got 1 carbon coming off here. We've got 1 carbon coming off the second. That's what I drew. We've got 1 top and bottom, and then we've got 1 on the second and 1 on the third. Any others that you draw or try to draw will end up being one of these. So there's only 4 isomers of the original, or 5 ways that you could draw hexane. And it is inappropriate, probably wrong, for me to draw without the hydrogens. Had I asked you to do this on an exam or a quiz, I would want you to draw in all of the hydrogens. I'm not going to ask you really long problems where it'll take a great deal of time, but this is just kind of going quickly, showing you what they would look like. But I would expect you guys to draw all the hydrogens. Cyclic alkanes, you can have alkanes that are in a circle, not necessarily a circle. The one see over here on the right is actually in a triangle shape. That'd be cyclopropane, highly unstable, but whatever. The general formula for the cyclic ones, the ones that bond back on themselves, is going to be CN2N. It's not going to be 2N plus 2. It's just going to be 2N. The simplest cyclic alkane is going to be propane, or cyclopropane, excuse me. You can't bond back on itself with only 2. So 3 and beyond, 3, 4, 5, 6, 7 carbons and so forth. There are things called alkyl groups. So those are things that contain carbon and hydrogen only, that are bonded to the longer chain of hydrocarbons, and they have prefixes that go with them. So the prefix for 1, so this is just, wow, this is just 1 right here. So 1 is meth or methyl. METH is the prefix for meth. 2 would be eth, 3 would be prop, and then beyond that, it gets a little weird. 4 would be butyl. If there was a group of 5, which is highly not likely because we're not going to have hydrocarbon chains that are that long, it would be pentyl. And we'll talk about those prefixes a little later. But when you have something attached to a longer chain, you end that with YL. So if we went back up to our isomers up here, and we have this one right here, we actually have a 5 carbon length, and then we have a methyl group, which I'm circling, coming off of it. So a single carbon branched off of this would be referred to as a methyl group. That's just a single carbon group. Had it had more than, let's say it had 2 in a row, it would be an ethyl group, a propyl if it's 3, and so forth. So alkenes and alkynes, alkene, ENE, stands for something that contains a double bond. We'll get to alkynes in a second, but they contain a triple bond. Alkenes are unsaturated hydrocarbons. The general formula is the same as the cycloalkanes, which is CnH2n. That's for only 1 double bond in the molecule. If it has multiple double bonds, you can't use the general formula. It's only for only 1 double bond in the compound. The carbon atoms of alkenes are held in place, and so they don't move as easily as they can't spin. The double bond with the sigma and the pi bond hold it fixed in place. And so you can have different sort of different types of isomers for these. You have kind of right and left hand facing isomers of these. What it's referred to as cis-trans isomerism. And so if you have the one up here on the top, which I'll circle up here on top, this one up there, that's a cis, meaning that they're on the same side of those carbons, but that carbon-carbon double bond won't actually twist. It sticks together. And so it sticks together and stays in that direction. The double bond can't spin like a single bond can. And so you get these fixed positions. If they're on opposite side, then it's called trans. So here we have 1 on opposite side, that's trans. And up at the top, we have 2 at the top, that would be cis. And that cis and trans show up in the naming of these molecules as well. Again, on your AP exam, you're not going to have to name these, but you should be able to recognize them. I don't know that this would have any, these are both nonpolar molecules, but they would have, they would mix together. They would mix with other nonpolar molecules. So it says draw both the cis-trans isomers of pentene, C5H10. So I'm going to actually draw pentene kind of real simply. So pent is the prefix for 5. So that would be 1, 2, 3, 4, 5 atoms in a row. It says pentene. So you don't know where that double bond is. The double bond could be on the second carbon. It could be on the first carbon. It could be on the second carbon or whatever. If they don't tell you what numbered carbon it is, then it's on the first carbon. So this is carbon 1, carbon 2, carbon 3, carbon 4, carbon 5. But if they tell you it's just pentene, then it would be on the first carbon. That would be the same thing as calling it 1-pentene. Yeah, so 1-pentene. Now what we're doing is now we're drawing all the isomers of it. We're only drawing the cis-trans isomers of it. So you can't have a cis-trans isomer if this is going to have a hydrogen and a hydrogen, right? It's going to have, you know, it's not, it needs something with a chain. So what it's going to have is it's going to be somewhere in the middle of those. So there's 5, it would be here. So in this way, we can actually have something that doesn't just have hydrogens on both sides. So this would actually have a hydrogen on it, and this would have a hydrogen on it, and this would have hydrogens top, bottom, and out here on the side. So the carbon has a valence of 4 or 4 bonds shown. What I have drawn up on the top is actually the cis. If you can see it, it's got a hydrogen down, and then it's got the backbone, the carbon chain going up on both of those. It could also be drawn sort of like this, would actually be kind of better. You could draw it. I told you I would say what shorthand was, or condensed structural formulas were. Condensed structural formulas where you put all the hydrogens together with the carbon, like CH3, you know, and over here I would write CH2 and CH3. So CH2 and CH3. That's a condensed structural formula without showing all the bonds to the hydrogens. And it's okay to write them this way as well. You wouldn't want to do that on the center carbons because you want to see the trans and cis isomerism. This one, of course, would be cis. If I were to erase the top and go and draw the trans, I would have, let's do the methyl group up top, hydrogen down here. And then on the other carbon, I would put the hydrogen up top and the remainder of the chain down here, this ethyl group, so to speak, there, even though it's on the backbone. So this would be the trans isomer. This would be the cis. So showing you what they look like here, they've done a better job doing their angles than I did, but it's condensed structural formulas. And so the cis 2-pentene, meaning that's, okay, so we'll get to this also, we'll do this, practice this, but the 2 tells you which carbon it's on. So if this was the first carbon, this was the second, the double bond starts on the second carbon. If we look on the other one, 1, 2, it starts on the second carbon. If we were coming the other direction, this would be the 1, 2, third carbon. You could call it cis 3-pentene, but you wouldn't want to do that. You always want to put the double bond closest to the side that has the lowest number. So the shortest distance to the double bond when you name these. We'll get to some of those rules in a bit. So yeah, there's those 2. Alkynes, the last one will have a triple bond. So the first one that can have a triple bond obviously be ethyne. Eth stands for 2 carbons, and so it would just have, you have to have 2 carbons to have a triple bond. You can't just have a single carbon. That wouldn't work. The general formula here with only 1 triple bond is going to be CN H2N -2 for that one. The carbon atoms around the triple bond, they have, of course, sp hybridization, and all of these are going to be linear, at least referring to the middle 2 carbons. The outer carbons, depending on how long the backbone is, can have lots of different shapes, but across the 2 carbon atoms, it would be linear. Same with the, not the same, sorry, with alkenes, they would actually have sp2, and then sp3, of course, with the alkanes with tetrahedral structure. Tetrahedral structure. Okay, so the nomenclature for this, the way to name these is International Union of Pure and Applied Chemistry is what IUPAC stands for. but they're the ones who determine kind of our naming system for hydrocarbons. And we'll go through these rules, even though I've kind of explained a few of them as we went through the PowerPoint. But for naming alkanes, alkenes, and alkynes, you name the longest carbon chain in the structure first. So if it's cyclic, you're going to use cyclo, but if it's 5 carbons long, you're going to call it pentane. If it all is single bonds. If there was a double bond in there, you would end it in ene, and it would be pentene. Or if it had 6 of them, it would be hexane. If it had a double bond in the hexane, it would be hexene. You're going to name in alphabetical order the groups that are attached to the chain that you named in step 1. So you'll use prefixes if you have multiples of them. You won't use mono as a prefix. You'll just say you have a methyl group. You won't say monomethyl. But if you had 2 methyl groups, you'd say dimethyl. If you had 3, trimethyl, and so forth. You need to indicate how many of each of those groups there are there. You need to number the carbon atoms in the longest chain consecutively from the end of the chain that contains attached groups with the lowest total numbers possible. We'll do some of this. So if you name from one end and it has a bunch of numbers, and you name from the other end and it has a bunch of numbers, add all the numbers up and find which one gives you the lowest. That will be the correct name of that structure. Assign to each group you name in step 2 the numbers indicating the positions, like I said, on that main chain. If the compound contains double or triple bonds, name the longest carbon chain containing the carbon-carbon or triple bond from the end that is closest to that double or triple bond. If it ends in ene, it's for a double bond. If it's yne, it's for a triple bond. The position of that double or triple bond is indicated by a number right before the name of the chain. We'll do this too. So if it's on the second carbon, it's 2-pentene. So it'll be a 5-carbon structure with a double bond starting on the second one, like I showed you up at the top or on the previous slide. When you assign numbers in the chain, you're going to start numbering from the end of the chain closest, like I said, to that double or triple bond. Now, here are the prefixes. Now, these are all in an ane because they're all, alkanes, but their prefix here is meth, M-E-T-H, ETH for 2, prop is for 3, bute is for pent, 5, hex, not sex, hex is 6, hept is 7, oct is 8, known is 9, or non, some people say known. And then dec is going to be 10. So what we're going to do is we're going to go through and name a few of these. I'll name a couple of them, and then if you want to hit pause and do them on your own, that would be wise to get some practice, and then come back and watch me do them. Let's do the first one. So first thing you've got to do is identify what the longest chain in the carbon is and any substituents or groups that are actually bonded to it. So if I went, don't do anything, just watch me for a second, but if I went straight across here, that's 4 carbons. That's not actually the longest chain. It looks like it is straight away, but it'd also be 4 going this way. And that's actually not the longest chain. The longest chain here starts down here and goes over here. Or if you like, it starts on the right and goes to the bottom. It doesn't matter. But that is 1, 2, 3, 4, 5 carbons. This is carbon 1, carbon 2, carbon 3, carbon 4, carbon 5. So the prefix for 5 is pent. They all have single bonds, so the ending would be ane. And there are 2 things located on it. I like to circle them. There's 2 groups there, and they are methyl groups. So I put methyl in front of the pentane, and then you have to tell me how many methyl groups there are. There are 2. So we would say dimethyl, and you have to tell me which carbons they are on. No matter which way I numbered this, from the bottom over or from the right down, it would be the 3rd carbon. So they're both on the 3rd carbon. So I do 3, 3, telling me where each one is, dash dimethyl, and that should be one whole word there. I kind of messed that up. Dimethyl pentane. And that would be the name of that compound. 3,3-dimethyl pentane. So there are 2 methyl groups, one on the 3, the other one is also on the 3. And then the longest carbon chain is 5, so pent, and they're all single bonds, A and E. Boom. The other one is a little different. We haven't talked about chlorine groups or fluoro groups or other things that this would be a hydrohalic hydrocarbon, but anyway, it's got hydrogens and halogens bonded to it. So there's a halogen on the top and a halogen on the bottom, and the longest carbon chain goes this way. Let's use my highlighter. Goes this way. And they've used condensed structural formula, which is totally fine. They're just not showing all of the hydrogens on the outside. But this is If I number it 1, 2, 3, 4. If I numbered it from the other way, it'd be 1, 2, 3, 4. But remember, we want to go to the side that's going to give us the lowest number possible. So the one that I have on top is actually the correct numbering. So the prefix for 4 is bute. They're all single bonds, so it ends in A and E. There are chloro is what we call these. If it would have been fluorines, they'd be fluoro. If they were iodines, they'd be iodos. But anyway, this is chloros, chlorobutane. There are 2 of them, so you'll need dichlorobutane. And you got to tell us where they are. There is one of them on the second carbon and another one on the second carbon. And so this would be the name of the structure. 2, 2, both on the 2, dichloro, 2 chlorines, butane, 4 carbons, all single bonds. Go down here and check our work. 3, 3 dimethylpentane and 2, 2 dichlorobutane. We did great. So here are a couple others. Go try them on your own if you want to hit pause and just write them real quickly. If you don't, you can just follow along with me. First thing to do is find the longest carbon chain. This way would be 5. This way would be 6. So this looks like a swastika. Okay. This would actually be correct here. And if I look, I've got one group here and one group here. These have 2 carbon groups each, right? And the prefix for 2 is eth. So these will be called ethyl groups. If I go through the longest carbon chain, that is 6. So the prefix would be hex. They're all single bonds, so it's A and E. There are 2 ethyl groups. Numbering from the side shortest is going to be 1, 2, 3, 4, 5, 6. So they'll both be on the 3rd carbon. There are 2 of them, so I'll call it diethyl, all one word, diethylhexane. And then they're both on the 3rd carbon. So it'll be 3, 3 dash diethylhexane. We do commas between numbers and dashes between numbers and letters. And then any letters that are there all get squished together in the same word. So let's try this one. The longest carbon chain here, you could get creative and go woo, 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 woo. That would be fine. But it is 1, 2, 3, 4, 5, 6. Any other way I go is going to give me a different number. What if I go this way? 1, 2, 3, 4, 5, 6. You could do that. It'll give you the same result as what I did here. I was just being weird. But if I go this way, it's 4. If I go 1, 2, 3, 4, 5, that's only 5. So it matters which one you choose as your longest carbon chain. And so this one we could go whoop, 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 whoop. That would be 6. If I number these, this is 1, this is 2, this is 3, this is 4, this is 5, this is 6. Prefix for 6, again, is hex. They're all single bonds, so it ends in A and E. By all single bonds, I mean between carbons. So between the carbons are all single bonds. All right. And then I have 3 methyl groups. They're all single carbon chains, right? Oop, that's not one. Silly Tolan. 3 carbons. So those are methyl groups. And there are 3, so I say trimethylhexane. And then you got to tell me where they are. They're on 2, 3, and 4. So this would be 2, 3, 4 trimethylhexane. Checking my work down here. 2, 3, 4 trimethylhexane and 3, 3 diethylhexane. Good job. Still going. Again, pause if you want to do it on your own. Longest carbon chain here is going to be boop to do. Could have gotten a little weird and creative if you like and said it goes this way. It doesn't matter. They'll both work. I'll go back to the way I had it before. So if I number them, this is 1, 2, 3, 4, 5, 6, 7 carbons. I have 2 groups on it, and they're not the same group either. So this would be 7. The prefix is hept. They're all single bonds. The ending will be A and E. I have 2 different groups. One is an this is an ethyl group because it's got 2 carbons. Eth is a prefix for 2. This is 1 carbon, prefix is meth, so it's methyl. Ethyl comes alphabetically before methyl, so it will be the first one that I have. So the second one will be methyl. You got to tell me where it is. It's on the 2nd carbon. And then I have an ethyl group on the 1, 2, 3, 4th carbon. Had I numbered these from the other direction, had I started down here and gone 1, 2, 3, 4, it still would have been 4, but the other one would have been the 6th carbon. 4 plus 6 would be 10. Here, 4 plus 2 is 6. So this is the correct naming. Oop, I messed up my phone. This would be the correct name here. I wouldn't name it this way because I would get higher numbers if I added them together. Yeah. Oh, didn't erase anything. So on this one, the longest carbon chain, boom, straight across. Could have gone all the way over and down. It wouldn't really matter. I have 2 groups that are attached to it. They are both methyl groups. So this is a methyl group, and so is the other one. I do have a double bond here, though. My longest carbon chain is 1, 2, 3, 4, 5, 6. I don't know why I went up and down, but whatever. 1, 2, 3, 4, 5, 6. So that prefix would be hex. There is a double bond, so it's ENE. To tell me where the double bond is, you put it right before you named the chain. So 2-hexene tells me all of that right there. Tells me the backbone, the chain. It tells me where the double bond is. Now I have to say where the methyl groups are. There are methyl groups. There are 2 of them, so it's called dimethyl. And you also have to say which ones they're on. They're on the 3 and the 5. Now, somebody out there is going to go, no, wait. If I add, 3 and 5, that's less than 2 and 4. It is, but you are the double and triple bond override where you number from. So you have to number closest to the double bond no matter what. Even if all of your substituents, your little side chains are all the way at the very end, you still have to number from the side closest to the double or triple bond if one is present. So there we go. Let's go down and look at my work. 4-ethyl, 2-methyl heptane. Good job. 3,5-dimethyl 2-hexene. Good job. Oh, these are monsters. Okay, so we'll go through this one. So I've got, this is the longest carbon chain. It is 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons long. There are no double bonds, but I have this group, this group, this group, and this group coming off of it. So I got a bunch of stuff going on here. I'm going to run out of room on the page, but whatever. So the longest carbon chain is 9. If I number it from the other directions, I have 1, 2, 3, 4, and then I have something on 5, and then I have 2 things on 6. If I number from the other direction, I have 1, 2, 3. This one would be 4. Let's use a different color. Maybe that'll be a good idea. Let's use a different color. Let's use red. See if that works. 1, 2, 3, 4. The 5 is still the same. 6, 7, 8, 9. So let's add up the way with the black pen. So if I do that, it's 4, 5, 6, and 6. So that total is what, 21? If I do the red ones here, I've got 2 at 4, so 4, 4, and 5, and then 1 at 6. So 4 and 6 is 10. That would be 19. We should number it from the red side over. So that's going to be from the red side over would be better. So let's go ahead and name it from the red side over, and I'll take away my my numbering here. Oop, put that away. Okay, so it's fine. It's red. So yeah, we'll go 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9, the prefix is non. So I'm going to put non. They're all single bonds, so nonane. Don't need to number by double bond. I've got a methyl group here and a methyl group here. 2 carbon, which is ethyl group here, and 3 is prop, and a propyl group here. So alphabetically, propyl will be the last one, so I'll put it on there. I'm kind of working backwards naming them. Sorry, guys. I mean, if you wanted to start with ethyl and then go methyl, then go propyl, you could. I do it backwards so they all squish together easily. This would be on the 5th carbon. And then next, I'm going to have 2 methyl groups, so dimethyl. One of them is on the 4, one of them is on the 6, so that'd be 4,6 dash dimethyl. And then I have an ethyl group on the 4th carbon in addition. So this would be 4-ethyl. So it would be 4-ethyl, 4,6 dimethyl, 5 propyl nonane. That is insane. but it's possible. Yeah. If I go down here and look, we've got 4 ethyl, 4,6-dimethyl, 5 propyl, no name. Yeah, we did that correctly. So I'm gonna take that away. Oop, that's not the eraser. Take that away. Give me some space because this other one's going to be long, but not quite as long. Here, the longest carbon chain is going to be here, here, here. I could have gone up on the first one. It wouldn't really matter. It would be the same. But yeah, I've got a 2-carbon group here, which is an ethyl group. And I've got a 3-carbon group here, which is propyl. And I got another propyl group over here. So my longest carbon chain is going to, if I number from this side, it'd be 1, 2, 3. This would be 4, 5, 6. If I number from this side, it'd be 1, 2, 3, 4, 5, 6. So in this case, it wouldn't matter which way you name it because you get 4, 5, 6 and 4, 5, 6. So it's entirely up to you which one you want to name first. It doesn't have to be any alphabetizing thing to figure out your numbers. You just add them up. So there's probably 2 different numbering or naming ways that you could name this. Nevertheless, I forgot 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9. So it's known. It's going to end in A and E. I have 2 propyl groups and an ethyl group. So I'm going to put my dipropyl here, 3 carbon groups. If I number from this way, it's 1, 2, 3, 4, 5. So 4, 5. And then the last one would be on carbon 6 would be my ethyl group. Ethyl on carbon 6. This is carbon 6 and 7, 8, 9. So 6 ethyl, 4, 5 dipropyl, no name. You could have numbered it differently. You could have numbered it, what it would be. Did I do this right? Yeah, I did this right. Hey, I'll just show it to you. It could have been 6, 4, 5, or it could have been 4, 5, 6. It doesn't make any difference because the sum of both of those is the same. So either name is acceptable for that 9-carbon structure. So yeah, these were some for you to practice on your own after you watched me do all of those. Wanted to see how many we had before we got to day 2. Okay. So if you want to push pause and go ahead, that's fine. Otherwise, I'm going to start. The longest carbon chain here is in a circle. Doesn't matter. You're always going to name the circle. So this would be 1, 2, 3, 4, 5. So this would be cyclopent is 5, all single bonds, cyclopentane. And I have 3 things off of it. When you're numbering them, you just go around either clockwise or counterclockwise with the smallest numbers. 1, 2 here. If I did 1 here and 2 here, I would have had 1, 2, 2, 1, 2, 2, which would be a larger number than 1, 1, 2. So there are 3. So it's cyclopentane. I've got 1, 2, 3, and these are, oop, that's the eraser tolerant. These are all methyl groups. So I'm going to have trimethyl, and then I got to tell where they are. So I have 1, 1, 2 dash, sorry, that didn't fit. 1, 1, 2 dash trimethyl cyclopentane. Wow. Here, 1, 2, 3, 4, 5. So pent, A and E, 1, 2, 3 things on it. That'll be trimethyl. And they're on the 1, 2, 3, 4. So this would be 2, 2, 4 dash trimethylpentane. Yeah. So there's those 2. I'll kind of speed here and show you the others. Here are the last, I think those are, yeah, those are the last 2. So you can check your work on those if you like. But try them without me just doing them. Okay. I'll see you guys in the next video, which will cover a little bit more of the polarity and the behavior of the molecules. We'll also talk about other groups that could be attached to them, which are called functional groups. Okay. See you in the next video.